Super. So yes, thank you for having me. As Jean Kuhn pointed out a second time, that's a particular honor. And then I'm really happy to talk about such a topic, the geometric unitary Kudla conjecture, which was something that I've been thinking about a lot over the years on that occasion. So just to set up the framework for this talk, I was hoping to actually explain more or less the idea behind the conjecture, then how we normally prove this nowadays, because that's not the first conjecture in this family of conjectures that is proven now. And the method so far has always been the same. Um, and then I will also really try to give an overview just in light of time. I don't give so much details, but this shouldn't keep you from asking. I mean, I've in fact even have extra slides at the back of details of the proof in case you are particularly curious about individual points, then I can discuss those. But a priori, I would more like try to offer a bird-eyes perspective on this whole thing. So the first thing that we need to talk about, if we talk about the Kudla conjecture, is special cycles. And special cycles are, in the end, what you really want to study in this program of various flavors. So there's a lot to be said about this, but to keep things short, in the 90s, Kudla and Milson, in a series of papers, developed a theory of special cycles, and this is special cycles on Lemur varieties. We will later define them. Um, and they actually found that those are related to automorphic forms, or specifically Siegel modular forms and Hermitian modular forms at the time. And this was essentially finished, at least the first step of this program, was finished in the 90s paper in ESES, and that asserted that at the level of cohomology, so if you take the cycles and then you take their cohomology class and you take certain generating series, which we will see, then these generating series actually are Siegel modular forms or Hermitian modular form, and this phenomena can actually be explained at the level of theta correspondence, which really indicates why specific phenomena that are related to stable distributions and so on play such a big role in the topic till today. But then later, not so much later, in fact, Kudla suggested that actually these series are only a part of what we could truly get. Namely, he suggested that we should refine this to algebraic cycles. So the idea here is that you have this family of special cycles on a Lemur variety, and then you form the generating series. But this time, you do not take their cohomology class. Rather, you take them as algebraic cycles in the Chow group, and you write down the generating series of these objects, and then you assert that this would be a modular form. Actually, even the modularity statement now is even a bit more tricky, and we will come to that. But the idea is really generating series with values in Chow groups should be modular forms. So to understand this in more detail, of course, we need to define these generating series, and to define those, we need to define special cycles, and to define those, we need to define homogeneous spaces which they live on. So for this, let's first go to Hermitian lattices, which for the unitary Kudla conjecture are the starting point. And I will work over CM fields, E over F, but if you feel uncomfortable about that, which is very understandable in the talk because these CM fields are a bit subtle, then just think about an imaginary quadratic field. And what we also want then is a lattice, is a torsion-free OE module. Um, and at the infinite places, we have a signature P1. So if you are in the imaginary quadratic field setting, you're now done. You have P1 and nothing else. But if you are in the CM field case, then the other infinite places should have signature P plus 1, 0. So they are positive definite. And what I mean by these places is places of F, the ground base field. They extend to complex fields, but the signature is invariant in this case. So you just need to choose this for the places of F. So over Q, for example, in the imaginary quadratic case. And then associated to this Hermitian lattice, we will need these objects. We have this rational Hermitian space. Like very often you start actually with that and then fix a lattice in there, but for us, we can still do it the other way around. You can also tensor with R, that's totally fine. This is a bit of an awkward object because it somehow comes with various copies of a lattice at each of the infinite places. So perhaps not exactly what we need. And indeed, we rather want to work with this R minus. So this is one specific component, if you will, of this LR. Or another way to view it, and that's more systematic and really helpful because it reveals in a more obvious way the complex structure. You just take the tensor product here over the imaginary quadratic field or the CM field with respect to the embedding that finds the indefinite place. Um, and what I mean by this is you just pick one of them. So you have one place of the ground field, Q or F here, where your form is indefinite. And then over E here, you have two that lie above that. Pick one of them and be consistent in the future. This later also comes down to some choices. You just need to be consistent, then it's quite okay. But if you don't want to do that, you can also just take the tensor product over OF, but then you are still a bit uncertain about the complex structure, which in the first half of the talk won't make a difference, but later this is pretty important that you keep track of those things consistently. Long
Sorry,
story short, yeah.
is this place the place where L is indefinite?
Yes, did I yeah, indefinite place.
Okay,
So I
I see.
by in I mean the infinite place at which it is indefinite. Yeah. So when we have this complex structure, then we can go on and construct a symmetric domain from that. And this symmetric domain, as always in this topic, is the Grassmannian of the maximal, in this case, negative definite subspace. Well, these things have signature P1, so this is a domain of negative lines, actually. Maximal here is just a line. So you take the subspaces here in your L minus, and then you have the dimension of this W equal 1, the complex dimension, I mean, and you demand that it's negative definite. Of course, there's a zero vector, then it's equal 0, but apart from that, it's always less than 0, and that's what I mean by this notation here. So this turns out to be a homogeneous space for the unitary group. I'm not going to really define this, but I think you can understand what a unitary group would be. It's the linear transformation that preserves the structure that you have underlying, in this case, the lattice, or if you take the R points, then just the reunification of the lattice. So now we have a homogeneous space, and so we are pretty close to having automorphic forms or modular forms. And what we still need is a subgroup of our lattice, and by lattice here I mean the discrete group, so the lattice in the Lie group. This should be a congruent subgroup. That's basically a non-condition. Only in the case of signature 1, 1, this is an axial condition, but otherwise it's guaranteed. So still, you need to include it. Stable, I won't say much about it, but otherwise the construction becomes a bit eerie. And anyway, we can always form direct limits. So this is also, in some sense, a non-condition. It means that your group gamma here acts trivially on the so-called discriminant form of the lattice, and I will later define that for you, but just so that you know where this plays a role. And neat is basically a regularity condition, so it means that you have no torsion eigenvalues in your group under the natural standard representation, and that means, among other things, that this thing is a nice object, it's smooth, it doesn't have conic singularities. So once we have this subgroup, we have the Grassmannian already, then we can form this arithmetic quotient as usual, and this is the starting point for modular forms as always. So this gamma dividing the Grassmannian, that turns out to be a connected component of a unitary similarity that doesn't play so much of a role for us today. I've decided to formulate that in the classical language here, but I point this out because the correct formulation of this is, of course, using adelic similarities, and then what we are doing here is, in fact, a component of axial similarity, and these similarities uniformize the adelic ones. So there's more technology, and there's good writes-up of this, but for today I thought we keep things simple so that we can actually all follow. So with this object now, we have basically our playing field. Inside this object, we want to define sub-objects, divisors, and cycles. Let's do that. But for this, to be a bit more accessible, I decided to actually do it in the classical coordinates to have it really, really nice. So over C, we are now working with the indefinite place. Then you can always bring your form into a normal shape. So I think the standard one is this one. Here you have the sum of the absolute value squares first, and then you subtract the last one. So this gives you a signature p, comma 1, quite evidently. And then negative lines here, because this last coordinate cannot be 0. they can be, after renormalization, be represented by vectors of this form. And so now you need a negative vector, so you can see what this means to be negative. If this is equal 1, well, then this part needs to be negative. So that's this coordinate. I changed the notation from x, which is just a lattice thing, to z. Now you have good coordinates. This is the coordinate that we normally use on, well, it's a complex ball, so on ball quotients. This is a known topic, actually. So everything that I've said so far really leads us to ball quotients, which you might have seen before. Just the special cases that you might indeed know, if not for the general case, then for p equals 1, this ball is indeed a disk. It turns out to be biholomorphic to the upper half plane, well, to what else? And then you recover elliptic modular forms. There's some subtleties about extra units and so in the imaginary quadratic case. And of course, if you have CM fields, then it's not exactly elliptic modular forms, then it's a bit more complicated. But in general, this is a very familiar topic, up to some finite index stuff, let's say. And then if you have p equals 2, you perhaps have heard of that if you work more in modular forms in general and not exactly in this part of modular forms. This is called Picard modular forms. So the most special case of complex ball quotients, and perhaps known because they are the most typical kind of modular form where you do not have such a good Fourier expansion. So there's some papers, quite nice ones in fact, where people compute these Picard modular forms, and one of the challenges is that you don't have these typical expansions that we use for this. So then you need to recover that through some Fourier-Jacobi expansions, which will come up later in our talk also. But this is so that you recognize perhaps some old friends. Okay, so we have now our ball quotient, or our ball actually. We have not yet done any quotients. So then let's actually do divisors on that, because we have not yet seen divisors. And the way you do these divisors in the field is you take such a quadratic form, let's say here, signature 2, 1, so Picard monoforms. And let's say simply we take this lattice here, 3 copies of an imaginary quadratic ring of integers, if you will, in the simplest case. And then let's take some lambda. You can take, in principle, whatever rational lambda. You want something rational, otherwise the object that you get out of this is not really nice. But if you have anything rational, for example, this one, 1, 0, 0 is very rational indeed, then you can take its orthogonal complement. And in this case, the orthogonal complement is rather easy to compute. It consists of all those vectors in this kind of presentation that I had introduced before, where the first component is 0. And remember, we actually normalized the second component. Perhaps I should have written set here, but I hope this is okay. So this sits inside our Grassmannian. It's a divisor. And it turns out in this special case, it's a complex disk. So what we have found here, and that's not a coincidence, if we take the orthogonal complements to some, in this case, positive definite vectors, then we get balls, but smaller balls. And this means that we kind of get this matryoshka of like the smaller and smaller ball quotients if we now start to work with this. Let's see how we do this. A priori, we would like to consider this ball, let's call it a sub-ball, in this arithmetic quotient. But the problem is, of course, it doesn't descend. And the reason is that the lambda is not stable. So no reason to assume that it descends to the quotient. One thing that you could do in this case, and that's a very valid move, this is called rational Hermitian divisors. In this case, one thing that you could do is you simply take the union over all your elements in gamma of this perp. You can also just take the orbit over these lambdas. If you define the actions correctly, this is actually the same. And then this sits indeed inside of the quotient. And what I will do without mentioning this further, I will always, when I have these divisors or then later cycles, I will always consider this in the Cloud group. I mean, we always work with algebraic equivalents of such cycles, and I'm not going to define those things because it's a bit technical, but it's important that this cycle is in some sense a representative for something that can be altered. But it is nice to think about it this concretely, I believe. So this is the first thing that now is an object on the arithmetic quotient. It is, however, not quite the object that we need to formulate the Kudla conjecture. So let's actually first do cycles in general and then try to do the special cycles, which are a bit more, well, special in fact. So what we could do instead of taking one vector, we can take several of them. Let's take a Lie tuple. Lie here is probably not the most typical choice of notation in the field. I do that because I come from modular forms, and there we denote this by Lie, so it's a Lie tuple of vectors. It could a priori be any rational tuple. And so then a cycle associated to that would be simply the intersection of all the cycles that we had before. In other words, simply these lines that are perpendicular to all these lambda I. And then in general, you cut down the dimension of this complement by G. This is the expectation. So this is a smaller unitary symmetric domain. Or of course, it could also be empty. One reason why it could be empty is that if you cut more dimensions than you have, if G is, for example, larger than P, then in general this would be empty. And in other cases, of course, if these lambda i's are not positive semi-definite, or even more general, if their span is not positive semi-definite, because then you would ask here for a negative line that is perpendicular to something negative in a space of signature P1, well, that doesn't exist. So in this case, it's empty, which in other words means we really have a strong positivity condition here on these lambda I. This will be convenient later just to make sense of some of the constructions so that you don't get lost too much there. But with this, actually, we can now introduce a bit more general notation. It's not needed here, but it perhaps makes it easier to think about this. So these orbits that we have here, they can actually be now associated to these classes, bracket lambda. In here, the quotient of our rational symmetric space to the G's power, and then we quote out the action of G on those tuples, simultaneous diagonal action here. And so then you take the union of these things, lambda prime in this class, and that's a rational Hermitian cycle now instead of a divisor. Okay, so the expected dimension of this would be Lie, or rather the rank of something that we are going to introduce next. Let's do that. Namely, these rational Hermitian divisors are not quite part of the Kudla program. They are kind of a building block, but what we really need is a bit more average thing. And for this, we need two objects. The first thing is the discriminant form. This is the quotient of our dual of the letters by our letters. And here the dual, I have defined this as those lambda in the rational Hermitian space, so that for all the elements in the letters, the pairing, which a priori is an element in the integers, or in E, and then you apply the trace here down to Q, and that should be an integer. This is one way to define it. You also find different definition, but that's I find this nice because I like to go down to that. It's an easy object. So this is the discriminant form. And here recall that we had this notion of stable subgroups. So actually, stable just means that this group gamma acts trivially on this quotient. That's why we need it, so that we don't have an action on this discriminant form that will now play a role in the construction of our divisors. And then the second thing here is the moment matrix. And really what you want here is the scalar product, and you normalize it. You normalize it in such a way that here in the codimension 1 case, so G equals 1, you just get the square norm of a vector. So this is a scalar product, and then you always have this factor 1/2. There's no magic here. It's just a normalization issue. So it turns out this is actually a Hermitian matrix. So Hermitian here means that you're invariant under the stagger, and this dagger is just the complex conjugate, and then you transpose. This is a natural object for Hermitian matrices in this setting. So then you put this dagger on top, just the way you always denote invariance, and you take the E points of this. It's rational in this case, because we started with something rational lambda here before. Okay, so this now are two objects, and let's just very quickly inspect their relation to the group gamma. We assumed simply that gamma acts trivially on this, so that's stable. And actually, it turns out if you have this unitary group and then you act on these tuples of gamma, of lambdas, well, that preserves their scalar product. So in other words, our gamma preserves the moment matrix. So we have two invariants with respect to our group here. This is important in the next step. Namely, what we are going to do is we simply take the sum over all those rational quadratic or rational, not so, rational quadratic, rational Hermitian cycles that have given invariance. So a set of mu and t for those discriminant classes and moment matrices. That's just the sum over all these rational lambda. which in the discriminant form are the same as mu, and then have a given moment matrix. And that because the discriminant class and the moment matrix are invariant with respect to gamma actually does descend to the arithmetic quotient. And just a remark here, we have this mu here. This comes from the Weil representation. To correctly formulate the conjecture, one needs the Weil representation. In fact, when you formulate this in the adelic setting, it becomes a bit more natural. But this is here the classical formulation where you like just record these individual lambda mu's for later use. Okay, so now what we have done is we introduced this symmetric spaces. We have the action on that to get an arithmetic quotient, which gives us something like modular forms there. And then we got sub-objects on that. And now, in fact, we have sub-objects that are really associated to two invariants that you might have seen in connection with modular forms. So there's perhaps a chance to formulate something like a generating theories that should be modular. And that's exactly where we are now. So we define the following series. Theta Kudla. I write this theta because it takes the role of a theta series. And we sum simply over the G tuples of our discriminant form. Take a formal vector element here. So this is just to separate the components. It's kind of a vector valued modular form. And then you have the classes here. And here you take this ET tor. And this is a formal series a priori. So I write this analytically because I'm really not a friend of these Q to the T notation type of things. But it really should be noted that this is a formal series. So what we do here is we take the matrix trace of our product, T times tor. Tor will later be defined. For now, it's some variable that you might have seen in the Siegel modular form setting. Or if you're completely unfamiliar with that, then just think of the elliptic setting and you still get something out of that. In that case, the trace is trivial. And you simply have a product here. And so this is an element that actually is in E tensor R, the realification of E. And we now take the trace with respect to F. Notice the difference. So what we do here in the background secretly is that we non-canonically extend this trace by choosing a family of complex embeddings of E over each of the embeddings of F. This makes actually the notation amazingly smooth and nice, but in the beginning might be a bit confusing. Be careful throughout the work, because if you ever confuse these embeddings, your statements become wrong. But if you don't confuse them, they become actually very nicely readable. So this is something that I pretty much like, but I want to warn you that there is a certain danger of confusion. There's another aspect that we need to talk about, and this is here the expected dimension. Of course, this should be ideally a codimension D cycle, but it's not always. In fact, the dimension of this, if it is non-empty, is rank T. And in this case, then, we simply take here a hyperplane, essentially. So the dual of the Hodge bundle is formally correct here. And we intersect this cycle simply with that. And that now gives us codimension D cycle. And so all these objects here live in the same Tau group. And we have a formal series of them. And so we have a formal Fourier series. This is the Kudla generating series. And we are going to make a statement about the modularity of this very generating series. Let's do that, actually. So the conjecture says this Kudla generating series is a Hermitian Hilbert modular form. Says something about the weight p plus 1. And it's for the Weil representation, and to be more precise, for the incoherent Weil representation. I'm not honestly going even to define this Weil representation. It's simply you take the nearby definite Hermitian space, incoherent then, and then you get a Weil representation for that. That's the correct one in this case. And if you walk over imaginary quadratic fields, you don't need to care about that. There's ways or tricks, so to speak, to get around that. But in general, you cannot really avoid this complication. So you need to work with the incoherent Weil representation here. That's correct setting. But okay, it's some representation. That's all that I want to say. And we won't need more than that for the purpose of this talk. So this is our conjecture. This object should be a modular form. But if you read this conjecture, you will notice there's a slight problem. What does this even mean? I mean, this thing is in general infinite dimension. So let's clarify this. The coefficients of this Kudla generating series lie in this Tau group. Here I need to tensor with Q, or I can tensor with C. It doesn't matter in this setting because modular forms are over C here. And these Tau groups are not finite dimensional. So a priori, I just take a linear functional L and I apply it to my Kudla generating series, which means I apply it coefficient-wise. And then the assertion is actually that this thing is a Hermitian Hilbert modular form. But once I have proved this, I can do much better because of the modularity I know. well, finite dimensionality of modular forms is a very general statement, and it's also true for Hermitian-Hilbert modular forms for this space here. So now what this statement here should say is that there's a finite set of modular forms, for example, take a basis, and then for each of them, a corresponding class. And so you have this finite sum of modular form times one class, and this finite sum has a Fourier series expansion. We will see that later. And so that sum decomposition, that finite sum decomposition, that should recover the Kudla generating series. That's the statement that we are going to prove in the end, or like how I like to read this statement. But what we really need to prove is this. Like there's no technical way around this applying the linear functionals, at least not that I know of. Okay. I think this is a great point to have a opportunity for questions if there's any. Well, then let's see what we have. In the divisor case, we actually have prior results. So here, in this case, the omega appears only in one coefficient. That makes it a bit nicer. And so the theorem then is by Liu and also by Hoffman for imaginary quadratic fields that this divisor generating series is indeed modular. So the conjecture by Kudla is correct in this divisor case. So this is what we had. This is all the 2010s. 2011 and 2014, if I remember correctly. So relatively recent, but also not super recent. It's not like the latest results. We have some solid understanding of this. The construction, by the way, between those two is very different. So Erik Hoffmann, he uses essentially something that goes back to Borchert's via explicit construction. That is also somehow the reason why he's locked into F equals Q, by Yifeng Liu. He uses an idea that goes back to the Yuan Zhang Zhang paper, where you use a specific isomorphism and vanishing of some cohomology classes. So that is very different methods, but the Liu method here is the more general one. That one is able to give us the CMKs. I'm not aware of any way to modify this approach to the CMKs, although that would be, I would be happy if I knew. Okay, so this is the state of the art, in fact. So we can directly then go to the main result. And the main result is, of course, as you can expect from the title, that also the general conjecture is true. So we have an integral Hermitian lattice here over a CM field. It can be any CM field. And we want, of course, a signature P1 here at one infinite place and the definite one in other cases. Otherwise, the proof method doesn't work. Like, of course, you would still expect something nice otherwise, but the proof method that we have just does not work, ever. Um, and well, in this case, then actually this Kudla generating series turns out to be indeed a modular form, as we said. Of course, we still have not really defined this space, and we are going to do that. But what this really should tell you is that these cycles, these special cycles, are actually pretty finite. Like normally a priori, we don't even know whether this object is finite dimensional. But now we know that, for example, the span, this is one corollary of these things, that the span of these things is a finite dimensional subspace of the Tau group. But there's actually a corollary of that, which I should probably not call a corollary because it's actually a theorem in itself, but it's a nice thing that follows from this one. Concerning arithmetic cycles. So I wanted to mention this. This is the arithmetic inner product formula by Li Liu. And so what you do here is you want to construct arithmetic cycles. Once you have the generating series, well, this is a tensor product of a modular form times Tau group, so why not take the Peterson inner product? This is an analytic object, you can do that. And so that should give you an element in the Tau group, and it ideally would encode information of the modular form that you started with. And that indeed is the case, and it's essentially proved here by Li Liu, apart from the fact that they needed to assume modularity, which now is proved. So that part of the proof is no longer a hypothesis. And what you get then is that the intersection product of these arithmetic cycles, that can be related to a special values, or actually derivative of L series, and kind of the kind to cross-sag here. So this gives you, in particular, non-vanishing of specific cycles. There's a lot of things to be said here also about the special cycles that I personally find super interesting about the non-vanishing of cycles. But via this inner product, for example, you do absolutely get that specific cycles, provided that the L series does not have vanishing at least two. If that is not the case, then you get also non-vanishing arithmetic cycles. That's pretty nice, I think. So let's actually think about what we need to do, because we are halfway through the talk. We now understand, well, not really understand, but we have an idea of what the Kudla conjecture would be, but we have not yet even started to proving it. It turns out to prove it, we need to set up another half of the talk. So the normal approach to prove these things nowadays is you have the divisor case. So you can do this with Borchardt methods or with Yuan-Zhang, and then that would lead you to the paper of Yifeng Liu or Eric Hoffman. And this is the divisor case. And then in the thesis of Zhang, Wei Zhang in this case then, there was this idea that actually this is already enough to get something that is quite reminiscent of the correctly modular object. And so this gives you a formal modularity statement. We will be more precise about that. In fact, you see that on the slide. It turns out this notion is a symmetric formal Fourier-Jacobi series. That's a word nowadays used for that. And so Liu already did that for us. So we know from his treatment via the ideas of Zhang that this Kudla generating series in the unitary case is indeed a symmetric formal Fourier-Jacobi series. And so what we would do, and as I said, this is the way that we prove all these statements at the moment, we just show that the symmetric formal Fourier-Jacobi series is a Hermitian-Hilbert-Moller forms. And that's actually now what we're going to do next. Well, this first, we need to define these formal Fourier-Jacobi series. This is like the object that we want to now study. So let's define that. And for this, we first need to define the space that they live on. I still owe you the definition of Hilbert modular forms. And now this will come. So let's recall that E over F is a CM field. As I said, you can actually take an imaginary quadratic field, but the truth is I will avoid this in this talk simply because I want to avoid stating the growth condition. But if you know the field, then you know when to add growth conditions. So in that case, you can just think about imaginary quadratic fields. This is more of like an alibi here to make this slide shorter for me, but it doesn't prevent you to take this simpler imaginary quadratic field case if that's what you feel more comfortable with. And so the Hermitian-Hilbert upper half space, this combines what you have for Hermitian forms, and then it combines also what you have for Hilbert modular forms. So here let's look at the imaginary part of, in this case, some matrix, in fact. So you take the tau minus the conjugate transpose of it, and then you normalize it correctly. That turns out to be a symmetric form over the base field F here. And so actually it makes sense to ask here in the condition in the definition of this Hermitian-Hilbert upper half space, it makes sense to ask for positive definiteness here. This is an object in F. And so we want those tau in the realification of E and matrices over that, such that this thing, which is an object over F, that this is totally positive definite. At each of the places it's positive definite, or if you work in the imaginary quadratic case, this is just over R, and then it's positive definite in the normal sense of good old symmetric quadratic forms. Yeah. I will not for you define these special unitary groups. As I said, it's just the stabilizer of some form. In this case, you take the standard form. There's some normalization issues, but it's very similar to Siegel-Moller forms, and it wouldn't give you much if I define this group. What you need to know is somehow the structure or the axes are very similar. So you have, and this depends on what this Lie refers to, there's a certain block decomposition in this Hermitian form, and then correspondingly, you have a block decomposition of your matrices, of these elements of the special unitary group. And it turns out, if you write this thing here, because here we wrote this E, tensor R, and this is like these are actually matrices and elements with entries in OE, although the group itself is only defined over OF. But so you know what it means to multiply those things, then you can also add them, take inverses, and so on. So this is well defined. You can also think about those things as copies of various matrices in upper half space. That's totally legitimate, and you can do that. Just again, you need to choose then a set of complex embeddings for your CM field. And once you've done that and stay to one choice, everything works out. But if you make a mistake, then things don't work out. Okay, so this is the normal action. At least it looks normal. Of course, there's more details. We need to be a bit more careful about the slash action, but we are lucky. For the Kudla conjecture, I don't need more than parallel weight. So we just take an integer in set, and then we define the slash action by here the C tau plus D, that you probably know. Then you take the inverse power minus k, the power minus k, But then you take also a determinant. Now this is an object in E, tensor R. And now I told you that I extend the trace non-canonically. I do the same thing with the norm. And of course, again, I need to choose the corresponding fixed set of complex embeddings of my field E. But when I do that, this is basically simply the product of those components. And then I use that as a prefactor for my normal transformation of F. And that's a slash action. There's, of course, many, many more slash actions, but we won't need them. And this makes it so much nicer to just think with this. I like that. So the next ingredient that we need is arithmetic types. As I said, I won't really define for you these incoherent while representations. The reason is that we don't really need them. Like we need some kind of tensor product decomposition in the actual proofs of those things, but that's already in Liu's work. So for our work here, it's actually just totally okay to think about an arithmetic type row, which I here want to define as a finite dimensional complex representation of our modular group, this case, the special unitary. And I want to have the finite index kernel, or more specific, actually a congruent subgroup, which in most cases not a condition, but if just to be very concrete here, that also in the case t equals 1, this would be actually a condition. So we have arithmetic types and weights, and the slash action for that. So that sounds like we have all the ingredients for a definition of modular forms, and that's indeed the case. So now we can define a Hermitian-Hilbert modular form of this weight k in Z and of a type rho as before. And what it is that we take a function from our upper half space to the representational space of our type, and we want the following covariance condition, so that if you apply the weight k slash action, then you get the same as before, but you need to multiply with rho of gamma. I write it like this. Sometimes you see this moved into the slash action. You can do that here too. It's a matter of taste on this level. I like it like this. And we want this for all the elements in our modular group. Do notice, by the way, I didn't remark on this before, but I have this special unitary group. You can do this for the unitary group. In fact, you could make the argument the unitary group is a bit more systematic, but I like adjoint groups, either out of habit or because one of the proofs in the paper actually becomes simpler. Both is a legitimate reason, but be aware that you need, for the full Kudla conjecture, you would later work with the idyllic unitary group, not with the special unitary group. Just not that this is super relevant for us when we prove conversions, but just so that you are aware of this like slight detail. In any case, with this notion now, we are also able to define what Fourier series are. We just take this sum here over Hermitian matrices T, and we have then our coefficients. They would be here in this vector space, and then this E tau, T tau. We have already defined that. It's just the trace, and then yet another trace, and e to the 2 pi I of that. So just the normal Fourier expansion. And everything is defined in such a way that this makes sense. Here, of course, you can like reduce the size drastically. I was very generous here to write E. This normally is discrete because of the modularity condition. But we don't need this for the exposition, so I'm brushing a bit over this. So we have the Fourier expansion, and this means at this stage now, we know what it means to have this Fourier series tensor tau group element, and then we can relate this now to the Kudla conjecture. One property that we will need, and which is kind of interesting in its own, is that we have this symmetry condition for the Fourier coefficients. So this comes from the Siegel parabolic here, this P of O F in my notation. You need here a general linear group element. You have a determinant condition. This just comes from the special, otherwise you can drop this. And so what you want is, if you have the T bracket A's coefficient, this is just Siegel notation. So T A or dagger A T A, this is like this. And so that's an action on these Hermitian forms, T. And you can recover the value here, this T bracket A, from the one at T by just multiplying it with a suitable normalizing factor and perhaps also accommodating some extra modular covariance via this A T transpose conjugate inverse. It becomes a bit unwieldy in the Hermitian setting. Many decorations, but it's some object. That's the point. We have some control over the symmetry. We can recover this thing from this thing. That's kind of the moral behind that. So this is a property. We need to remember this. We later will impose this symmetry. So this is something that you should remember. Symmetric coefficients of Hamilton modular forms satisfy a symmetry property. That's the word symmetric that we have for symmetric formal Fourier-Jacobi series. Well, there's a second part in this word, namely Fourier-Jacobi coefficients. Perhaps we go there. So first we need a block decomposition, H less than Lie. So we get this block decomposition. Here we have this tau is of size H times H, and the other blocks are of corresponding size. Do notice, as opposed to the Siegel case, which might be a bit more familiar for most people, you have a second variable W here. That has to do with here in the Fourier coefficient decomposition, you have the R bar. Otherwise, you get like doubly periodic functions. If you don't do that, then of course this is not what you want. So yeah, two variables as opposed to one. And for historical reasons, people write Z comma W, not WZ, like whatever. But it's two elements, and with this block decomposition, we can actually take a partial Fourier expansion of our Hamilton modular forms, just in the usual way how you would get a Fourier-Jacobi expansion. This is this expansion here. And then it turns out these phis are actually Hamilton-Hilbert-Jacobi forms. Now that's, for the purpose of this talk, this is almost only a word. I won't say much about it, but let's very quickly revise what they are. So we have here, this is where they live. The tau one is in H, and then we have here these matrix spaces. And then we have a Klingon parabolic inside our special unitary group. That defines this. And I define this here just via more or less this expansion. So if I could allow myself to go back, you just want that this individual term here, so to speak, without the sum should be invariant under the specific subgroup that stabilizes these terms. That's kind of the idea. The main point for you here would be that here we have this superscript Li minus H, and that indicates the Liness of our, well, related Hamilton modular form. So this is actually a construction that kind of lowers the Liness, and in this sense enables a kind of recursion, if you will. And that's actually why these things are important. So then a symmetric formal Fourier-Jacobi series here would be, I want to emphasize, formal series of this kind. Here, these functions, these are actually functions. This is our series, it's formal, and the objects here are Jacobi forms. And then we also want the symmetry condition on the Fourier coefficients. The Fourier coefficients here are defined via the Fourier coefficients of the Hamilton modular forms, via this block decomposition of T that I was mentioning before. It's a bit of a formal process. So these objects do not, these Fourier series that correspond to that do not converge, but the symmetry condition is a purely combinatorial or algebraic symmetry. So you can impose that one. And that now defines you this space of formal modular forms of genus Lie and co-genus H, and K and rho R as before. So this is the object that we are going to study. And so by Liu, actually now coming down to what we have to prove, Liu proved that if you have these functionals here of the tau group and you apply them to this Kudla generating series, then you get a formal Fourier-Jacobi series that is symmetric. This key codeliness is as bad as it can get. So there's as little convergence in there as possible, but still a bit. This is more than nothing. And this little convergence comes actually from the divisor case. This is where this stems from. And then the correct representation and so on. So this we know. That's also, by the way, the reason why we don't need to bother so much about the incoherent representation. Somebody else did that for us already. And we just need to then answer the question. We have this inclusion via the Fourier-Jacobi coefficient. Is this always an equality? And since there is actually cases where this has been proved for other groups, and in those cases we call this automatic convergence. So now I, of course, use this term still. Do these symmetric formal Fourier-Jacobi series converge automatically? This is the question. If we can answer this affirmatively, then we know that this is a modular form, and by what we had before, then we know that actually the Kudla conjecture is correct. And so now we finally at what I really wanted to do, or what I really have proved, automatic convergence. So let's look at this. The result here is that we are again still in the setting of Hamilton-Hilbert modular forms. We have this parallel weight. I've never even bothered thinking about the non-parallel case. Forgive me for that. It could be that the proof works, or it could be that it doesn't work. We have arithmetic types. And we here have the full modular group. This is actually something that I also need. I thought a bit about relaxing this, and I can say something about that in a second, but like full modular group for now. And then what is true is that every symmetric formal for each Jacobi series is indeed convergent, and then it also is modular. In this specific case for the full modular group, this modularity statement is actually not as easy as in some of the Siegel cases where it's a bit more elementary. One needs some K-theory computation, but it's true. And it's somewhat classical. So with stuff that has been done in the 70s, you can prove that, but it's a bit harder than in the Siegel case. So what we assert here is then this equality between the space of formal series and here the space of Kleinian series. Just some remark on the extent. So I was asked whether this would work in the Hilbert case. This does work. Actually, the proof is almost the same. It's in some sense easier. So the orthogonal case would also follow from via this technology. I've not written up the details, but I'm pretty convinced this should be easier, and I can actually tell you exactly. I did that for some people. I can tell you exactly what chain list you need to make. And the rest is more schematic. So somebody should write this up at some point so that we are sure, but that should actually follow. The modular group is a bit more involved. You could, for example, specifically in the Siegel case, you would definitely be tempted to make statements about paramodular forms, but there's other groups also in the Siegel, in the unitary case, that would be interesting. So the convergence statement in this case does actually work. And there, again, you hardly need any modification. But what is a bit more difficult is the so-called formal theta decompositions that later appears in the modularity conclusion. So for those things, somehow, I mean, about some aspects I have thought it seems to work, and we in fact have one statement where in the Siegel case, paramodular, it does work, just because people have written this up. We come to this later. But and I would be optimistic that this works, but one wants to be careful. On the other hand, I want to absolutely mention this because it would be nice to have this at some point in the literature. Then we know the extent of the method. Okay, so this is the main result. Let's look at what people have done before, because we are going slowly towards the end of the talk. It's time to think about our precursors. So the first time that I am aware that something like a formal convergence theorem was somewhat hinted, but it was absolutely not really done like that, was in a paper by Hiroki Aoki in the very early 2000s. He actually did something completely different, Igusa classification, but he did this for the genus 2 full modular group no types. There he has a certain dimension estimate that later then was realized by Ibukuyama Pur-Yen can actually prove automatic convergence in this specific case. So they basically adopt Aoki's argument and see, yeah, this actually has a very strong consequence. But it is a bit coincidental. So you really rely on a specific dimension estimate to be exactly another dimension formula. You cannot expect this in general. And so then Jan Brunier and I, we parallelly, and the good thing is with different methods, this was really good, we with different methods proved the Siegel modular forms case in genus 2 and any type. So Jan Brunier, he used actually an ampleness argument to reduce things to the Ibukuyama-Pur case. What I did was very different. I introduced some kind of algebraicity argument, which is also what we are going to use today. But this argument by Jan is also consistently used throughout the theory. So it was really helpful to have those two different approaches, which were still compatible. So what we did then is just add them together and do a lot of extra work. This is not only adding them. We had to do like a bit of hard work there. But eventually we got the arbitrary genus and any type for the Siegel modular forms case. So this is over Q Siegel modular forms, and that implies in that specific case then the orthogonal Kudla conjecture over Q. And then using these methods, Cha-Cheng Cha, who was a student of mine, he did the imaginary quadratic fields with norm Euclidean integers. So this comes from a specific vanishing statement that is a bit complicated in the original work, and that's just the scope to which it extends. So this is the earlier work. And then there's what I would call concurrent work. I mean, okay, Ibukuyama-Pur is by now like almost 1.5 years old, so it's not quite concurrent, but it's kind of the latest news, so to speak. And they proved the genus 2 Siegel paramodular case pertaining to this remark that I made about the modular group that appears in the theorem. So they actually, it's kind of interesting because I consider their contribution to the field the most important of this paper, a different one than they seem to consider. So from what I understood, they think the foluation argument that you will later see in the sketch of the proof is the important contribution, that there's a precursor of that in this paper. which was important, and it's undoubtedly important. But for me personally, a specific vanishing statement, which actually appears in some form or shape, even in a single author paper by Aoki, was much more important. It was then when I noticed that, like, some problem that I had in the theory and in the proof, that I could solve that through a different technique that is also like visible already in this paper. And they did this case. And that, something that I also really want to highlight is this almost quite exactly parallel work. I mean, in fact, I uploaded the first version of this paper the day when I noticed Aaron's paper, um, and he does code Linus 1 in only the imaginary quadratic field setting. But what is really amazing about his paper is that he has a very different approach to this. Just like in the historical setting where we had different approaches and then could combine this, I would be very curious in how far one perhaps can combine these techniques with the technique that I have now to get perhaps even more. So Aaron has previous work on real analytic forms, and the things that I do at the moment would never work with our current state of understanding for real analytic modular forms, simply because we do not have a good enough algebra structure. So perhaps there's something to be done by fusing them. So I wanted to really give a shout out to both people or both sets of work, because they are super important in the background of this work. But now, nearing the end, as they say, I think it's time to at least briefly remark on some key steps of the proof. So this is like, it's a long paper, but it in some sense falls into natural steps that build onto each other, or sometimes are even somewhat independent. So the first step is that you consider the trivial type. Just good old modularity, and then you form an algebra of your formal series, and you show that this is algebraic over the module forms. This is actually the case where I was stuck so many years. I was not able to prove a specific vanishing result that you need to prove this algebraicity, and now I can do that. And in fact, this is the first section in the paper. It's quite long, actually. I am very, very happy that we now have this statement. So this algebraicity was one of the key statements, and this type or a scheme of proof does not work at all without this algebraicity. While Aaron Pollack's paper, for example, would remove the need for this. This is why I like this so much. It's like really a new idea there that one should explore further. But let's stay with the algebraicity. So what Jan Brunier and I did originally was that from this algebraicity you get something about convergence in the neighborhood of the boundary and so on. That's one possibility, and that has to do with the fact that Fourier-Jacobi expansions are naturally expansions around the boundary. But actually what is introduced here in this work in a more formal way, and as I said, like it's foreshadowed also in this Aoki-Bugiyama-Pur paper, is foliation of your Chalmers or of the upper half base. I write it up, and you show simply convergence on rational leaves. And here you need some it's like a lot of classical Hecker-bound theory and reduction theory combined, but actually in a quite clever way, and it's a bit subtle. So from this you get then convergence, and this has a priori nothing to do with this algebraicity. It's just convergence on some foliations. Let me highlight that this is just a very classical thing that we know. If we study Chalmers varieties, it's not a new thing to study Chalmers varieties by restricting to smaller Chalmers varieties, typically then curves, but in this case it's actually not curves, it's a bit more complicated. But this is something that we know how to do, or like that this is a useful tool, and it turns out it's also super useful here. There's actually more to be said about the relation between this and this boundary approach that we used before. But what we need essentially comes in the fourth point. So let me first quickly mention, you use this to show that you converge against a meromorphic function. This is a place where you use the algebraicity, and there's a subtle detail here that really implies that you're only at meromorphic here. So you need a way to control divisors here. And that also is something that Jan and I had to do with the divisors. And this is the reason why this new foliation techniques is a bit better. Because in the Kudla Conjecture, you can go around that. You have enough information about the boundary, but in many of the other applications, like computation of modular forms or so, you really have only the expansions at infinity. And then the boundary is just not large, or this boundary strata, or component, is not large enough to see all the divisors. You need to control divisors here of this meromorphic function. And in the case of this foliation, this is just a transversality result that comes down to Borel density. And this is, by the way, the reason why I like to work with the adjoint group. Then it's technically a bit easier to do this. So in the other cases, you need to do this with an intersection with the boundary that becomes very, very subtle, as I had to learn. So this is then, at this point, we know that things are regular. And at this point, we know that the scalar valued ones are equal to modular forms. And then the incogenous one, this is something that we need here also. And so then now we have two independent reduction steps. So one is here this idea that goes back to Jan, just use amplitudes and some non-degeneracy to get down to trivial types. So this is one idea. You can also use this to use more general weights if you want to. This is the first important step. And then the second step, this is a formal theta decomposition. You need this to reduce yourself to cogenus, arbitrary cogenus from cogenus one. This is a super technical step, quite delicate in fact, but it's formal actually. That's why it's named formal theta decomposition. So this is the key steps of the proof. I think we are also slowly towards an end. So I think time for a brief summary. What we have done here in this talk, we have taken a similarity associated with a Milton lattice over an arbitrary CM field. We had to do something with the signature, so P1, and then otherwise definite. That's standard in the field just because otherwise our base case is not divisors. Then Leo, we noticed, had already proved that this Kudla generating series that we defined there is a symmetric formal Fourier Jacobi series. What I now proved is that these things automatically converge. So that confirms Kudla Conjecture. And because I really like this, as a consequence of that, you get arithmetic cycles and then these inner product formulas and so on. So this is the contribution of this talk. With that being said, thank you for your attention and I'm happy to hear your questions.